Okay, so I just wanted to review a bit, especially because when I was writing the exam, all the things that were actually a little stuck in my mind, like things I wasn't quite sure about, and therefore I'm fairly certain you may also have some of these mental wanderings. All that got worked out, so I wanted to review and point out some of these things. Okay, so review of time-dependent this or that for a time-independent Hamiltonian, because time-dependent Hamiltonians are hideous. And of course now I'm going to put a little, there's no time dependence. I'll forget that t minus t0 deal too. So that's the unitary operator that drives you forward, right, whatever. We went over this, and it starts out, so I'll bring t0 back, just to remind you, because this is the language that we use. No, the operator does its job, right? The operator is gone. So anyway, back in the language of, as we started out, and of course, if this A prime thing is an eigenstate of the Hamiltonian, you run into the weirdest thing. Which is that, look how easy this is. It's just either the I, it's just a number. It's just a number. Cosine, whatever this is, plus I sine times the ket, which of course we all know that may be its own issue to work with. Add the position operator or something, now it's a regular wave function, but whatnot. So recall that we started out deriving this, if it's time dependent, we had those Dyson series things, which again, I told you, I've only seen that once get brought up in a talk. Time independent is, when is that? Well, that's like when we're talking about a molecule just being a molecule. It still has a Hamiltonian, the Coulomb operator between electrons and protons and whatnot, and electrons and electrons. But we don't have any like light, which it has a time-varying electric field. We don't have it in some kind of EPR or NMR that's doing some funkiness. So time independent. We get to this, which again is like, oh man, I thought this stuff would be hard. And this is where you really get flummoxed, because we think of things as being, and let's say that this is the ground state. We think of things as being the ground state, but then unfortunately, as we also talked about, there's nothing dynamical. Expectation values for operators, whether they commute, whether they're the operator for which this is the eigenket, operators that commute with the Hamiltonian or don't commute with the Hamiltonian, whatever. None of it, no expectation value is time dependent. And that means that the world, the universe, is non-dynamical, which is wrong. Now, one of the answers that we talked about was that you create dynamics. One of the ways to create dynamics is to do things like take a electron in its bar magnet and bend it over from Z to X. And again, we talked ad nauseum about this. And of course, what do we get? We get things like the average. Now we're getting dynamics, and so of course I'm going to put a little t there to remind you that this is a time-dependent dynamic. So I've created a superposition state. Remember that if there's a magnetic field in the z direction, plus and minus are the states, but Sx is plus plus minus. So that's a superposition state. Superposition states do evolve in time. And we can create those using, magnetic field that points it up and a radioblast that turns it over. That's how your NMR works. And when you get this, then you get a dynamical, expectation. Now you're seeing an expectation value with a t in it. And of course, the angular frequency is just the difference between a high energy and a low energy state divided by h bar. Again, that's kind of, that will be the case in everything you've ever studied. But regardless, now, and I also wanted to point out that one of the things that always drives me crazy, other thing that arrow isn't right. Anyway, one of the things that always kind of drove me bonko nutso is when you go to talks that are PChem talks, and let's say that it's like a laser person, like a Bluesack, or Robert Gordon, who retired a while ago, so I don't know him, but you know, some of the big names in PChem are these ultra-fast laser people, and they keep talking about phase dependence, and it's like, what the hell is that, right? We've talked a little bit about how the phase relationship, well, again, let me just give you an example. I know I've already shown this to you, but again, it bears repeating. So that would be when you bend something over, I'm not necessarily married to putting this, taking the vector and putting it necessarily in the plus x direction. I can really put that in any direction. And so the difference between these two pictures is a difference in phase. Now, let me use my NMR example. Here's intensity over time, and now have all of you done NMR at some point? Yeah, so you know that the damn thing looks like this. And the reason it decays off is that that's just simply, so let's use NMR, so this is a magnetic nucleus. What'll happen is it'll spin around in the XY plane, but eventually it pops pointing back up, so that's why the signal decays off. So this is like case 1, and case 2 looks like this. It'll be, it's just out of phase. You see how they're different? There's nothing to it. Right, so you can wonder, like, you know, when you Fourier transform these in your NMR to get your NMR spectrum, they would be identical. In fact, when you're adjusting phases, people claim you know NMR, so I'm going to hold you to that. When you adjust the phase of the signal, you're kind of like mathematically turning this into that. That's one of the things you're basically doing. Ultimately, you get the same spectrum. So you may wonder, why bother? Now, you get the same spectrum because remember, a phase relationships really don't change the dynamics. The phase is e to the I times an angle times your whatever, times your operator, times your wave function. You know, you can inject it many, many ways and start talking about it, but it never really matters because e to the I whatever, when you're looking at an observable, the observables always wipe out imaginary stuff. So e to the I whatever turns into the number 1. So when I Fourier transform these, I'm going to get the same spectrum. So the fact that these are out of phase, have a different phase, just doesn't matter. So why are we talking about it? Because part of PChem is to get things perfect. You know, oh, these are the same, let's not worry about them. That's not what we do here. Right? If I want to describe the differences between these two, because like you give me the signal and I'm supposed to reproduce this perfectly, I need to be competent enough to know that the answer is that there's a phase difference. It's not that meaningful, but again, if for some reason the question is why are these not exactly the same, and we have an obligation to answer, there's your answer. So anyway, that's my spiel about phase. And when you hear that word used, phase relationships, you can just make this mental picture, even if they're talking about something else. That will still serve you well. Okay, now the next thing we talked about was Heisenberg relationships, where instead of evolving the states, we evolved the operator, which is a hell of a funky thing. And I think maybe just because of the mathematical complexity, we tend to do it that way. So whenever I read papers and whatnot, they will almost universally represent things in a Heisenberg way. The Heisenberg picture, remember it's called a Heisenberg picture. Okay, last time we talked about SX, so let me just remind you that we solved this by a product rule. It actually was not a particularly difficult derivation of all the things we've done. It was just kind of algebraically kind of sucky. Okay, we did this. The next thing we assume, again, for convenience, when I did this derivation, well, whatever operator you're talking about, and I have a little generic omega, and the Hamiltonian, they were both time dependent, so don't forget that. Now again, because we're not trying to blow each other's heads off here for this class, you'd actually, when I was in grad school, if this was actually time dependent, then you kind of have to take another class to be blunt. We've already talked about the difficulties of working with time dependent Hamiltonians, but time dependent Hamiltonians are not that common really. Molecules are moving around on their own without necessarily having time-dependent Hamiltonians pushing them. Okay, so for the purposes of this class, of course, this ends up being, and I'm going to now talk to you ad nauseum about, no, that's still time-dependent, sorry. And remember, I will, from now on, I'll be using parentheses 0 when I'm talking about operators like we're used to. Okay. Now the dangerous thing is now you've got to, here, let me rewrite the right half. Well, we solved this last time, but you see you got yourself a bit of a Bismarcker here. You've got an operator equal to its commutator. It's a differential equation. Now, remember, they're actually easy. It's not a double derivatives bring you into a world of mathematical pain that is sometimes insurmountable. This, you just bring dt over and integrate. Single differentials are always trivial. Double differentials can, often we see e to the ikx plus e to the minus ikx. Cool, often, sometimes we'll get lucky and it's easy, lots of times it's not. Anyway. Okay, now there's another mathematical pain here. This is some of the things that kind of got my own mind unstuck when I was writing the exam, because this class is hopefully good for all of us. Okay, and let me throw some highfalutin words at you, because I warned you about this. The problem with solving this as is that s of t may not commute with sx. Sx of t may not commute with sx of 0. So when it comes to solving, what you'll find it may or may not be equal to 0. Now I have to put a little question, equal question mark, because if t is 0, then of course they commute. But at some future time, see, I don't really know what this is. I don't know what sx of t is yet. I haven't figured it out. If I don't know what's in here, I don't know whether it commutes or not, because I don't know what it is. I mean, that's brainless. My question to you is, what does it mean for it not to commute? Remember I keep saying that in papers and talks? People keep saying, well, the operator doesn't commute. And you're like, oh. I get that means that this is not equal to 0. But there's implications, there's many potential implications, and so when someone says that, I don't know necessarily what they mean. Okay, can anyone tell me, what do you think? What does it mean for this thing to may or may, let's say it does not, if it does commute with itself. Anyway, the harder one to understand the implications thereof is if it doesn't commute with its future self. What would that mean in this case? Anyone? Not sure. And I told you that this is like, I'm glad I'm teaching this class because I'm starting to understand this stuff, because I got to make sure. Now, you'll come out of this class probably still confused just like I did, but I'm doing my best, all right? Any idea? Again, I never really, I don't know that I still understand it, but I think I get it a little better now. Tell you what I think? Because you're kind of all just sitting there. Let me tell you what I think. All right. Simple. All right, this is unbelievably, at a very low level, but still meaningful. You don't know what the hell this is. That's what it means. So, when you say it doesn't commute with its future self, that means this operator could look like freaking anything. In fact, because we already know what, we did this at the end of the class, Sx of t at a certain time is actually equal to Sy. Sx and Sy, remember our direct notation, spin, right? Stern-Gerlach, these are kind of easy, right? Plus, minus, minus, plus, all that. If Sx at a certain time is actually Sy, Sx and Sy don't commute. My point being that this damn thing could be anything. If I say it doesn't commute, that means that I have no freaking idea what this could be. It could be radically different. Okay, now as it pertains to this problem, if it doesn't commute with the initial operator that I know so well, then how the hell am I ever going to solve this? Because I mean, what I'm saying is, this thing's future is unknown to such a degree that I can never figure out this commutator. Now, at time 0, I happen to know what this is because remember the Hamiltonian is actually SZ because we put this spin in a Z field, in a Z magnetic field. So H is, hopefully you recall, because we put it in a magnetic field, it's actually SZ. Okay, and remember it's time independent. So this is H bar plus plus minus H bar over 2 minus minus. And that's H bar over 2 plus minus minus H bar over 2 minus plus, something like that. Anyway. Okay, so at time 0, I can figure this out, but at later time, I can't. So in other words, you are stuck, and there's no way out. Okay, so anyway, I just wanted to throw that at you. That is one of the examples of, oh, it doesn't commute. What does that mean? That's what it means. It means you're freaking stuck. Okay, so recall the solution to this problem is that, now I went over this last time, so I'm not going to remotely repeat it. Remember that since we've already made the Hamiltonian time independent, what you can do is factor the unitary operators. You can factor the unitary operators out, just like that. Now it's time independent. Now you have a shot at solving it. And of course we know that Sx, Sz is minus I H bar Sy. And so what do we get? We get angular frequency over I H bar. I forgot where the I H bar comes from, but anyway. I H bar Sy. Of course, the I H bar Sy comes from the commutator. Things that we figured out a while ago. Okay. And of course, this is equal to there we go. And likewise, we do the same thing for Sy. And of course, it would just be really the same thing. Wherever you see a cosine, there's a sine. Wherever there's a plus, there's a minus. Where there's an x, there's a y. Where there's a minus, there's a plus. Don't presume that, all right? It just always tends to work out that way. Whenever I'm doing a problem like this, I'm always checking to see that, sines turn to cosines and whatnot. Okay. Now, on the handout, I show you how to solve this thing. I didn't want to spend class time on it because it would take me the entire time. And of course, what you end up with is Sx at time t. Gotta turn my handwriting a little off. Is our very well known Sx minus Sy. And I won't put Sy. It's basically the same thing. I mean, I did it last time, right? I don't want to spin it down. It's not repeating what I did. I always do that to a fault. Anyway, so, and you see it makes sense, right? At time 0, cosine is 1, so Sx at time 0 is Sx at time 0. So, and then we see later, see what I was telling you why you can't presume that it commutes with itself, because at a certain time, 2 pi over the angular frequency, it will turn into Sy. So there you go. Anyway, just to march down memory lane, and from this, Now, let's say that you're, oh, again, I always, when I'm doing an expectation value, I must tell you what state for which I am applying this, all these developments. And this is h bar over 2 goes. And this wouldn't be horribly difficult, just again, direct notation, which I think is I hope it's kind of fun. I hope you find it kind of fun. It's really not that hard, right? So anyway, so there you go. That's just a march down memory lane. And I wanted to summarize it because I'm going to do it one last example and then that's it. But this is really related to what I have on your take-home exam. And again, I think it's fair because we're always building up anyway, so I might as well just drive it to the end. Okay, spin operators. I know that this one's a little funky because you have a couple differential equation. Again, the handout solves it. I've got an example. Spin normally is way easy. So now let's go back to like electrons and whatnot. So what I'm going to do is a free particle. So, sorry, free wave. What am I saying? I almost said free. I was actually defaulting towards the book's language, but I've been using free wave. Free wave particle, right? Easiest thing possible. But now we're in a world of P and X. And of course, P and X, and I've got commutators. I almost forgot how important commutators were before I was doing this class. Okay, so the Hamiltonian is T squared over 2m. And there's no potential energy. Okay. Now, again, we're going to assume no time dependence. Okay. Now, I want to point out, I'm going to point this out a couple of times because when I was writing your exam, I started running through this hamster wheel of circular logic. And it got me really flummoxed until I got myself out of it. And I want to intentionally mess you up and then fix you just like I fixed myself. Actually, Mike Stife told me this. He told me when he was writing answer keys, he would make them, we all make mistakes. And he used to erase it and then fix it, right? Like he would think it's logical. But then he realized he stopped doing that. He would intentionally start making a mistake and then instead of just erasing it, he would leave it, maybe cross it out or something, but he'd leave it to show people how you go in the wrong direction and you pull back out. So I'm going to do that with you as well. When it comes to solve, so we're going to solve this Heisenberg, this, that, time-dependent operators for free wave. P and X, because that's all there is. And I'll show you where I got a little flummoxed when I was writing your exam, so this will also be helpful for that. So what I need, of course, is the time-dependent momentum and position operator, because that's really all I got, right? Hamiltonian is remember, it's just h bar squared k squared over 2m. And the wave functions are e to the ikx. So we did this like 2 months ago. Okay, now what have I got to, all right, so what could I possibly even be working with? Well, of course, let's solve for momentum over time. So let's solve the Heisenberg form of momentum operator. H bar P. Now again, remember it's not P at time 0. You can't do that. It's P at time T. And unfortunately, this could lead to a hideous complication. And you got to be careful with that. Okay. Now, here's the thing. Now, it turns out that I'm going to show you that this is 0. And so there is no time evolution to the momentum operator. But I'm kind of cheating. Let's say I don't know that. P of t may not commute. Here, let me should have done this. Momentum operator at a future time may not commute with the momentum operator as we've always known it, minus IH bar ddx. The momentum operator at a future time may be more complicated, and it may not commute with momentum as we've been doing it. In fact, maybe momentum has an x in it. X and p don't commute. If this doesn't commute with itself, it may not commute with h. Meaning that if it commutes with h, remember, then all of this is 0. This becomes stupid easy. Stupid easy. We need to qualify that. If it does commute with h, it's 0. If it doesn't commute with h, I have no freaking idea what to do, because then I can't figure this out. If I can't do this, then I can't do that, which gives me the answer. So again, you see that if p of t does not commute with itself, at say time 0, if it's going to misbehave, then I have no way of solving it. Again, that's the big picture. Okay. Now, the way to solve this is exactly what I did before. Remind you that that's time independent by definition. Okay, so I just want to remind you, because maybe you need to do this on your exam, because I've given you a p and x deal based on what I'm doing now. Okay, there we go. Okay, now I can deal with this. Now I can deal with this. Okay, I'm going to be explicit and write it all out. I'm writing kind of small. I can kind of not do that. Let me blow this up. I don't know why I'm writing small today. Okay. Remember, any operator times a function of itself is 0. Remember, what this is p cubed over 2m minus p cubed over 2m. That's 0, right? No tricks. If there was an x here, that would be a problem, because then this would commute. These two would wipe each other out. But if there was like a plus x squared, like a harmonic oscillator, then it's not 0. But anyway, so we're doing baby steps. We're going to work with a simple problem. So this is 0. Okay. Now here's where I got myself in a bit of a rabbit hole. Now again, it turns out that like on your homework, you're not going to have this, by the way. It's not going to be 0, so I'm just going to tell you that. Here, let me right, 0. What's the integral of 0? Well, let's do this right side. So 0, so then it ends up being t, so it's t minus 0, so it's t, right? It's just 0. I'm just messing with you people. It's just 0. Right, so therefore you got p of t is equal to p of 0. I just wanted to be formal. I just wanted to mess with you. Okay, now here's what I want to not have you get on that hamster wheel that I did. On your homework, exam, actually, on your homework, on the last question and exam, you're not gonna be so fortunate. It's not gonna be equal to, it is gonna evolve in time. It's gonna be p0 plus, I forgot. Anyway, it is gonna evolve in time. Okay. All right, so what? It's really not that hard a question, but it won't be this. Okay, here's where I got on the hamster wheel. If this evolves in time, should I be doing this? Should I be doing that? Sorry, again, my handwriting is so bad today. Oh, it's Monday, isn't it? Yeah. Okay. Now again, don't write this down. I've messed up what I've written before. I'm just trying to prove the point, so don't write this down. Again, on question 5, and on your exam, you're going to have time evolution to the momentum operator. It's really not bad, but there will be time evolution. If momentum is evolving in time, should I have done this? Should I have actually left it as P of t? And if I left, sorry, that's a screw up, that's a screw up, right? If this is P of t, then it actually has to be P of t in here. And now I've got myself in a hamster wheel, because now I've got P, yeah, that sucks. So I've got, then I guess I have P of t here. So I guess that is 0. But then if I do this, then it's P of 0, P of t. Round and round and round and round. I'm confusing myself right now. Again, just want to point out, if the nature of the problem isn't such that if momentum is evolving in time, should I have done this? Because I'm telling you, if I don't do this, then this is freaking hard, like impossible, like I cannot solve it. And that seems like a problem. So what do you think?
It's again that we came to the what we did last time here. In order to do that, the Hamiltonian said that it's p squared by 2m. We have defined that P of t is P of 0. Because we are saying that Hamiltonian is not time dependent, right?
Right. We're saying Hamiltonian is not time dependent.
Yeah, then we can have the P of t in that equation.
No, that's a cheat. That's a cheating.
No, we have said that this h of t is
No, hold on. My point is, what happens if this is not true?
Then the Hamiltonian is not time dependent. If Hamiltonian is time dependent, then the whole things will get in a lot of comments.
And that's actually wrong. See, when you do what you did, which is what I did, by the way, so I'm not trying to be critical, I did the same thing. You run into a problem where it becomes unsolvable.
Yes.
Right, so that's bad. Now you can solve it. So let me give you the answer. Because, yeah, no, I swear, you did exactly what I did, by the way. Okay. It turns out that because the Hamiltonian is time independent, remember, what did I say here? I said kinetic energy is p squared over 2m. Why would that change? Right? That's, 1/2 mv squared. That's solid. That ain't changing. Right? I don't have this thing in a spinning electric field. I'm just saying kinetic energy is kinetic energy. Okay, so logically, we do this. We're not going to let it evolve in time. By definition, it doesn't evolve in time. So by definition, we keep this P0 squared over 2m. By definition. Okay. So then how can momentum evolve in time? The answer is, this is like a funky mathematical problem, right? Normally, I want to use time evolution operators to evolve a state, because that makes sense. Things move, and so I should model them as moving or doing whatever. But this time, we're going to say that the states don't evolve in time, we're letting the operators evolve in time. So when I'm doing this deal, I'm solving for this, but it's kind of independent of that. I've decided, because kinetic energy is 1/2 mv squared, that this isn't changing in time. But due to the mathematical, like the way I set this up to solve it, this is evolving with time. But I've kind of decoupled these, right? I have this weird, funky mathematical derivation that allows me to do this, but this guy is not really part of that. It stands by itself, and as I had stipulated, it's independent of time, therefore it is truly independent of time. So that allows you to go here. And once you're here, you're home free. So anyway, that'll also be more clear if you need help. If you look at the handout, if you need help on the exam, you may do exactly what you just did, which is what I did. And again, I'll walk you through it. I'll talk you through it again. If you find yourself going through that rabbit hole. Okay, now it may be a little bit more clear. Let's do position, because position, we're going to run into a harder situation with position. Position, the commutator will not be 0, right? So that's going to be your position. And remember that this is done on the handout. On the handout, I did the spin one, but then on the second page, I did what I'm doing right now, because I'm going to not do part of it. But anyway, let me just set it up and you'll see. Okay, so momentum is trivial, okay, but now let's do position. Position turns out to be a little harder. As usual, just don't have to think about it. Although I have to figure out where the hell, there we go. Again, I stipulate that as being 0. Okay, let's see. Again, I'll write out the unitary operator. So I'll be a little bit easier about this. X at 0, which is just X. And this okay. Those blended together. Okay. Now, X and P, we know that the commutator of X and P is minus I H bar. No, it's I H bar. Anyway, it's not 0. So right, so now we have a situation where it's not 0. This is also P squared. Okay, so that's also, that actually adds a little layer of complication. Now, it turns out, now this is what I did on the handout for you. This is what I did on the handout for you. I showed you that this commutator is, where the hell, anyway. What was there an IH bar? Yeah, IH bar. Yeah. Anyway. Is that right? Is that messed up? Oh, maybe it was messed up. No, that's right. Okay. So on the handout, I did that for you to show you that. It's not that bad. I just didn't want to spend, again, 20 minutes doing a proof. That's really just freshman algebra. So anyway. Okay, now if that's the case, then you've got, and I'll revisit, I actually going to do this twice, but let me just power through this. What you got is the unitary operator. Look at that. You know what that is? That's P of T. Okay. Now wait a minute, what's P of T? P of 0, right. So, now wait a minute, okay, on the exam, let me go ahead and tell you. Sorry, I misspoke. Momentum doesn't evolve in time, but T does, but position does. Position does, and it ends up being a little complicated. Sorry, I misspoke. Position evolves in time, so does this one. Anyway, so you have to be careful the order that you solve these. And so I have, on the exam, I made certain that I wrote, do this one in part A, do this one in part B. And I did that because you have to do this in a certain order. So notice in this case, you had to do it in a certain order. I had to do P first, and then I had to do X. Okay, now therefore, X at 0, X at T. Again, I'm just being very careful with my calculus. And therefore, the position operator times T is the position operator times 0 plus the momentum operator times 0 over M times 16. Okay, now, I think on question 5 of your present homework, I technically told you to solve this, so don't worry about it. Maybe I already did it, sorry. I just thought I'd go ahead and do it for you. That question that's really a Mathematica deal anyway. That's been quite a bit of time in Mathematica.
thank you.
Given the equation for to find that that extra section.
Huh?
So you already given the equation to find the answer from the in that mathematical section.
Except I don't use the same wave function.
Oh, you just need to change it.
Well, I know,
And this is
but
the-
Mathematica is a biz knocker sometimes.
Yeah.
Yeah, I mean, it's, all right, the number one thing is EXP, capital E. If you forget the capitals, it doesn't, I don't know what, it won't tell you. Like, it's obvious what's wrong, well, it's obvious after a half an hour screaming at the damn screen.
Move them.
Well, that's, yeah, I mean, when I first was learning, before class, I was learning it, so, because I knew I'd need it for this class, and I spent a few hours stuck on EXP with a lowercase e. And the damn thing, and now I know, you hit solve, and then it just spits out, integrate, it spits out integrate.
Yes, it does nothing.
So now I know that. Anyway. Okay, so I just want to point this out. And then, of course, what you do for the things, I'll actually kind of end on. I do want to, actually, I want to, I'm going to do this a different way. This right here, I just want to remind you of those Poisson brackets. I just want to, just go through that again, just for the hell of it, because we're kind of at a good stopping point here. We're kind of at a good stopping point here. Wait, what do I want to say? What do I want to say about this? Seems like I wanted to say, yeah. So when I have you do this, remember what I'm really doing is having you do this. And this guy is where it sucks, right? This isn't so bad. So this is going to be x0 is just x. Now, remember, you can't necessarily assume, assume that xp and px are different. Guess what? They are not different. Sorry, God, they are different. You may look at the cross term, right? When you square this thing, you square that and squared. When you FOIL this out, when you square this, you may want to say, oh, xp, there's two of them. So 2xp t over m, sorry, t over m. You may say, oh, that's 2xp t over m, but no, xp px, they will not return the same thing. Okay, but here we have a t squared x squared. Okay. And the average value then, of course, is the complex conjugate. Right. So each one of these damn things, so you plug in the formula, you give it a function, define the function, and then this one is, of course, with Mathematica. And this one is again, I know this looks hideous, but in Mathematica, once you get it set up right, it's all quite easy. Then, of course, you've got, for this one, then you've got on and on and on. And remember, p squared over m squared is minus h bar squared, a double derivative. Anyway, so that's how you solve that. And then the last thing I wanted to mention was just a reminder about Poisson brackets. So when it came to solving this, remember that for any function of p, it turns out your book says this, it ends up being, here, I know I'm out of time, so I'll stop here. And I'll wrap up. There's actually one or two last things I need to talk about, but I'll just save it for next time. Okay. It turns out that I worked through this SOD completely. I worked this out on the handout, but it turns out that it will always be true that you'll just end up with the derivative. When you run into x and a function of momentum, which you run, the reason that you need to know this is because you run into it all the time. It's just IH derivative of the function. So x p squared over 2m is just IH p over m. Anyway. Okay. And then I didn't quite get as far as I meant to, but we'll just, they'll give me fodder for next time. Next time we're going to do harmonic oscillator, which you may have think there's not much to talk about the harmonic oscillator, but there's a whole completely different way of doing the harmonic oscillator problem in grad school, which you're going to see next time. Yeah? Yeah, all right.